What I want to do today is to present to you a method that we've developed for inferring diversification rates without a molecular phylogeny and without a fossil record. And so the question is, where did we get the temporal information? And the temporal information we're getting from the geologic evolution of the islands of Hawaii. And so here, I'm going to overspeak this. I want to remind you that the Hawaiian Islands formed over a hotspot, and that the Pacific Plate carries them progressively further away, and as they do so, they shrink. One of the key aspects of this is the fact that the islands grow faster than the ability of the crust underneath to accommodate the extra weight. So when the island stops growing, the islands continue to subside for some duration. That'll become important in a moment. And so what it means then is that the islands are older and smaller as one proceeds to the northwest. But I'd like you to note here that the age of millions of years here are actually too young, and I'll get to that in a moment as well. So in effect, what we have then is the same evolutionary process operating on each of these islands individually, and there are different ages. And so the fact that I've got the same process operating at 4 different times gives me my temporal information. And that's what I'm going to exploit now to calculate the diversification rates. So I wanted to now derive for you the way I've computed these rates. And so I'm going to start off with something pretty elementary, and that is Catherine Wilson's Biogeography. And so there is a intrinsic species accumulation rate, origination, immigration minus extinction, and a carrying capacity. And of course what happens is that as species richness increases, diversification slows down until you reach the carrying capacity. And so of course that's logistic growth, and there's the mathematical equation for it. So what I'm going to do now is derive for you the shapes of the curves that have a time-varying carrying capacity according to the geologic evolution of the islands. And so what I'm going to do now is have the carrying capacity and the intrinsic rate increase as the island grows rapidly, with a maximum species accumulation rate and a maximum carrying capacity, and then more slowly, that's going to decay away again as the island subsides and erodes. And so what I'm going to do now is write down for you the equations of that and then solve them. So it's fairly simple addition, adding in the time-varying rates, the time of growth, and the time of decay. And the next slide, if you're averse to mathematics, you may close your eyes. The solutions are not pretty, but they're solvable. So what I want to do now is give you a sense of what logistic growth looks like then, with time-varying carrying capacity according to the island ontogeny model. And so here I've got the rapid growth and the more slower decay. And I've arbitrarily in this diagram picked a carrying capacity of roughly 20 species. So then it depends on how fast the plates diversify. If it's very fast, it roughly follows the carrying capacity. If it's slower, these are the shapes of the curves. So what I'd like you to note then is there's a wide range of patterns. Now I have the species richnesses on each of the 4 major islands, and so I use those species richnesses to work out which shape is the best shape. And I use the absolute magnitude of those species richnesses to get the magnitude, the maximum carrying capacity. So that's the way I'm going to get those diversity parameters out. And so just to remind you then, so that here's the raw data, which then consists of the species richnesses of 14 clades that are monophyletic on the island, predate Oahu, etc., etc. And so I'm going to use the shape of those curves to estimate those diversification parameters. Just want to make you a note that this is very similar to the general dynamic model of island biogeography of Whittaker. But there's some interesting differences. The first is that in Whittaker's cartoons, they always have the species richness basically following the carrying capacity. Doesn't have to, as I've shown you. The second one is they made a subtle mistake, is that if the species richness is going to decline, the species richness at the end always has to be above the carrying capacity, not below it. And so if you look here, you can see then that this trajectory has a spectacular diversity undershoot. It's only at equilibrium briefly, and then an overshoot. And it has to overshoot, otherwise it can't decline by logistic growth, if you just think about the logic of it. Okay, so now what I want to do is show you how I estimate the shape of the carrying capacity curve for each of the Hawaiian islands. And to that I use geologic data. So here's a map of the islands of Hawaii. So first of all, for maximum area. So I indicated to you that the islands grow rapidly, and then as they move off the hotspot, they slowly subside as the weight of the island depresses the crust underneath. And what it means is that we can actually pick up the size of the maximum size of the area. The reason is that lavas erupted underwater have a much steeper angle of repose than lavas erupted on land. And so it turns out that if you look at contour maps, there's a change in slope, shaky, in this dark orange here. That shows you the old coastline. It's about 1,000 meters down for most of the islands now. So I get the maximum area by tracing out that contour line. Notice here at the leading edge of Hawaii, where there's active volcanism occurring, there is no change of slope, or change of slope at the sea level. So the island has grown so fast, the crust underneath it hasn't yet subsided. In terms of the time of first colonization of the island and maximum area, that's a little more difficult. The issue with the age of the islands is, of course, that the island, when it first emerged, that surface is now underneath all these accumulated lavas, and actually about 1,000 meters below sea level. So people use the age of the oldest lavas, which is well after the age of the formation of the island itself. So what I chose to do instead is to try to bracket the ages. I'll show you the bracketing of the ages now. So what we have here is geologic data. This is the rate at which the plate is moving, 10 centimeters per year. This is the distance of the volcano from the current source of active volcanism. And so that gives you an estimate of when the volcano was born. So the first habitability has to be after that. And then the end of this dark blue here is the oldest known lava, which lies on top of the oldest lavas. So I can bracket the time of origin of the island somewhere between there. So in here and here and here, etc. So that's what we did at that end. In terms of time of maximum height, we used a change in the composition of the lavas. Whoops. Indicated by these colors here. And basically the island stops growing approximately the time that the phyololitic lavas turn to alkali lavas, and I won't go into the petrology of that. So then, the summary diagram looks like this. So here then is our estimates of the time of origin of each of the islands with the error bars, the maximum area time, and then the current area now. Now these are the geographic areas. I need to now convert those to carrying capacities, and to do that I use species area relationships. And so here, for example, is data for plants on the island showing the exponent for plants leading up to big islands, which is hopelessly out of equilibrium. Here's another one for the honey creepers. So now I have my diversity trajectories. Now I'm going to work out what the best value of the diversification parameters are. So there's my shapes again, and now what I do is show you the way the analysis looks by looking at, say, initially one clade. So this is the lobeliads. These are the species witnesses from Hawaii, Maui Nui, Oahu, and Hawaii. And now I want to test various models to see which one fits the best. So the first one here is just pure exponential growth. That is a fixed diversification rate, and it fits really, really badly. The oldest island should be the most diverse. It's not. It's the least diverse, or almost the least diverse. Maybe this is just a single carrying capacity that's independent of area island. That doesn't fit so well. Maybe there's a carrying capacity that's proportional to the area of the island, and that fits better. And then there's the island ontogeny model, which in this case just absolutely nails the species richnesses. And what I'd like you to note is that diversity has gone up and down on the older islands. So the orange here, hard to see, is the AIC weight of the island ontogeny model. And here the 14 clades. Clades, so the more orange there is, the better off the support. And so for some clades, like the silver swords, silver swords is basically equal weight for all models. In some cases, the models doesn't fit particularly well. So just sort of show you another one here, terrestrial beetles. And again, a single K doesn't work. Even an island-specific K doesn't work, but the ontogeny model works better. So that gives you a sense of what it looks like. So what I can do with the model fit then is estimate the maximum carrying capacity, normalized by island area, and the diversification rate. And with those, I can then estimate the instantaneous species accumulation rates. So here are the values of the carrying capacities and the diversification rates for the different clays. And what I'd like you to note, they're completely uncorrelated. So the species richness is uncorrelated with the rate of diversification. It's up on really young islands. So people who use diversification rates to estimate why there's so many species, I think, are barking up the wrong tree. Sumasaurs. There's the wonderful phylogeny of Bruce Baldwin and Mike Sanderson. Here's the lineage through time plot, and like a lot of molecular phylogenies, it shows this little kick up at the end, and it shows a positive net diversification rate. They're doing great. Now the model. So there's the net phylogenetic morphological rate, and then here's the diversity trajectory computed using our ontogeny model. Really high rates early as the island expanding, then those rates drop, so it's hyper-exponential, then it drops to zero, and then for most of the history of the clade, it looks like it's actually been gently negative. And the current diversification rate is negative the value of the rate you estimate from the molecular phylogeny. The current diversification rate is negative the rate that you estimate from a molecular phylogeny. I published a paper called 5 Biological Laws recently that I'll try to not so say. So it's really hard to estimate diversity dynamics if you don't have a fossil record, if you only have a molecular phylogeny. So then, here then are the diversification rate trajectories for all the clades and all the islands. On Hawaii, they're all positive. The island is still growing very rapidly. They haven't filled up the ecological space. On Maui Nui and Oahu, 11 of 14 clades are actually already negative. And on Kauai, most of them are gently negative. So it suggests that most clades on most islands are actually in slow evolutionary decline as deduced by the island ontogeny model, not what you would have inferred from the molecular phylogeny. And with that, acknowledgements, especially Tiago Kental. This work builds on earlier work that we've done looking at red queen and mammals in the Cenozoic, and a wide range of other people. Okay, thank you. Yeah.
Did you take into account that malaria was introduced and caused some birds to go extinct, and that humans may have impacted the diversity on the islands?
Right, so it's almost impossible to adjust the species richnesses for human-induced extinctions. Yeah. That's just hard. If we had that data, we would use it. Yeah. So if the model doesn't fit so well, it's because the model isn't very good, it's because the raw data is not so good. Yeah. And that's just plain hard.